Welcome back, everyone. Today we're getting into 9-7 on Taylor polynomials and approximation. So the idea here is that we're approximating some function by using a polynomial. So for example, if we consider the function f of x is e to the 2x at x equals 0. Now if I just wanted to find a flat line that would just go through that single point, I could just create a polynomial that went through 0, 1. Notice here f of 0, e to the 2 by 0, which is 1. So I could just find a polynomial that goes through 0, 1. But if I wanted to get a little better idea of what was happening, I could also take a look at the rate of change in the function at that point as well. Rate of change, that is derivative territory. So then I'd be looking at f prime of x, in this case 2e to the 2x. And at x equals 0, f prime of 0 then is 2e to the 2 by 0, which is 2. So now I could say, okay, well then I want a slope of 2, and I want to contain the point 0, 1. So I could look at y equals 2x plus 1. If we take a quick look at these, let me clear them out here. Take a quick look at these. I'll put in y1, I'll put the original f of x, the e to the 2x power. And I'm in the -5 to 5 window on both x's and y's. Just hit your window key, x min, x max, -5, 5. Do the same thing for the y's. So there's our original. If I wanted to just go through the point, I could even just put y equals 1. Not super helpful. Contains the same point. But if I go up a power and put in my 2x plus 1, I get a little bit better of an approximation of what's happening at least near that point. Right now, though, it's still completely flat. E to the 2x, obviously a curve. Well, then I can throw in the idea of having the same concavity at that point. So concavity, that is second derivative territory. So f double prime of x here would be 4e to the 2x, and f double prime of 0, 4e to the 2 by 0, which is a 4. So then I would want not only our slope equal to 2 and containing the point 0, 1, I would also want our second derivative to be worth 4. We'll call p our polynomial. I want p of 0, p double prime of 0 to equal 4. So the polynomial function that will do all that, p of x is 2x squared plus 2x plus 1. It has all of the properties that we want. If I do p of 0, we still have our 1, so it contains the right point. P prime of x, 4x plus 2, p prime of 0, then is 2, slope of 2. And if I do the second derivative, p double prime of x is 4, so p double prime of 0, of course, would still be 4 then. So let me throw that into the mix on this same screen then. So on our y4, we'll put our quadratic 2x squared plus 2x plus 1. And you can see, at least in a small neighborhood around x equals 0, much closer approximation here. In fact, let me get rid of the couple of linear guys we have, and we can just see the curves playing together. So there's the original, and there's our curve. Notice, at least nearby, they do behave in sort of a similar fashion. You get too far away, though, they will diverge. They'll get further away from one another. So that's the idea here with the Taylor and later Maclaurin series, is that we're approximating what's happening on some other type of function by using polynomials. We do also have a special case if our function is f of x equals e to the x, and we center on x equals 0, then our polynomial p of x would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus etc. forever. And again, assuming we meet those two conditions, we're wanting to center it at 0, and we have just the basic f of x is e to the x function. That will match, and you can kind of test that out on your own, plugging in maybe a 5th degree or a 7th degree and the e to the x on the same screen, and you'll see that they do give values that are very, very close. All right, so let's get to then the general definition for a Taylor or Maclaurin polynomial. So we're assuming f has n derivatives at x equals c. Then the Taylor polynomial would be p of x equals f of c plus f prime of c by x minus c plus f double prime of c x minus c squared over 2 factorial, and then keep that pattern going. Nth derivative of c times x minus c to the n over n factorial. My apologies for the little detour I had to take for the hole in the page there. If we let c equal 0, then we have the Maclaurin series. F of 0 plus f prime of 0, and then x minus 0 is just an x, so x instead of x minus c, plus f double prime of 0 times x minus 0 is again just x, and we have our squared over 2 factorial, and then that one builds up the same way up to our nth derivative that we said we have at least n derivatives. So the Maclaurin is a little bit shorter, just in that instead of an x minus c, we just have x to whatever power. All right, so let's take a look at these with, we'll do an f of x equals, we'll do e to the negative 4x. And here, where did I pick the center? Let's start with the Maclaurin. We'll center it at 0. Nice, neat, pretty 0 there. So we can start with the Maclaurin. So then p sub n of x. My apologies, I should have had the little subscript here on these as well. P sub n tells us we're doing the up to the nth term. So p sub n of x for this guy, well, let's take a look. So f of 0 is 1. Plus f prime of 0. So f prime, of course, here, let me just sketch this out to the side. F prime of x, negative 4, e to the negative 4x. F double prime of x, 16 e to the negative 4x, and so on. So f of 0 is 1. F prime of 0 is negative 4 times x plus f double prime of 0, 16 x squared over 2 factorial plus negative 4 cubed. So notice here the 16, negative 4 squared, and so on. X to the third over 3 factorial. So our nth term, we would have multiplied n copies of negative 4 together. X to the n over n factorial. So that would be our Maclaurin polynomial. I'll just put Mac for short. Maclaurin polynomial centered at x equals 0 for f of x is e to the negative 4x power. So we don't always find just the general nth one. They may have us find specific ones. So this next one we're going to find p sub 0, p sub 1, p sub 2, p sub 3, and p sub 4. For the given function f of x is cosine x, and we're going to center on x is pi over 2. So we'll need up through a fourth derivative here. So I'm just going to make a quick little table off to the side here. So f of x we said was cosine x, so an f prime of x would be negative sine x. F double prime of x, derivative of negative sine would be negative cosine. F triple prime of x, derivative of negative cosine is sine. And finally f fourth prime of x, derivative of sine is, we're back to cosine. So we'll start with the p of 0. So p of 0 sub 0 of x. So this is, since we're not centered on 0, this is a Taylor, not a Maclaurin. So f of c, f of pi over 2, cosine of pi over 2 is 0. So our Taylor polynomial, if we're just looking at the 0 that is just the x-axis, y equals 0. So not a terribly exciting approximation. P sub 1 of x, we're going to go up to a first power. So then that would be f of pi over 2 plus f prime of pi over 2 times x minus pi over 2. And then we just fill in what we know. So f of pi over 2, we already established that that was 0. F prime of pi over 2, sine of pi over 2 is 1, and we have the opposite, so negative 1 times x minus pi over 2. So that polynomial turns into just opposite of x minus pi over 2. P sub 2 of x, f of pi over 2 plus f prime of pi over 2 times x minus pi over 2 plus f double prime of pi over 2 times x minus pi over 2 squared over 2 factorial. So over 0 factorial is over 1 factorial is also over 1. So that's why they typically, excuse me, do not include the denominators on those guys. Okay, so from there, we'll just use our little table to plug and chug. So f of pi over 2, we don't know that's already a 0. So f prime of pi over 2 by x minus pi over 2, that's basically our p sub 1. We already have that. So minus x minus pi over 2. And then plus f double prime of pi over 2. Cosine of pi over 2 is 0. Opposite of 0 is still 0. So we still have opposite of the quantity x minus pi over 2. P sub 3 of x, f of pi over 2 plus f prime of pi over 2, x minus pi over 2 plus f double prime of pi over 2, x minus pi over 2 squared, and then we hit the triple prime. So p sub 3 of x, f pi over 2, we know that one is a 0. We saw before this guy was a 0. We saw before this guy was opposite of x minus pi over 2. So the only new guy here is the f triple prime of pi over 2 over 2 factorial, and this guy is over 3 factorial. Still a 0 there. F triple prime of pi over 2, sine of pi over 2 is 1. So we have plus 1 over 3 factorial times x minus pi over 2, 180 cubed, and then just a little cleanup duty. So opposite of x minus pi over 2 plus 1/6 x minus pi over 2 cubed. Now, see if you can figure out why p sub 4 of x would be the same. I'm just going to leave that for you to figure out. See if you can find why p sub 4 of x will be the same as p sub 3 of x on this problem. Okay, so the next one, we look at another Taylor polynomial, and then comparing some decimal approximations. So we're going to find the third Taylor polynomial for f of x is we'll just do the cosine of x again. We'll center it in a new spot. We'll center it on x is pi over 6. I think the author may express it as c equals pi over 6. That c is in x value. So third Taylor polynomial, so we're looking for P3 of x. So that would be f of x plus f prime of x by x minus c plus f double prime of x over 2 factorial x minus c squared plus f triple prime of x minus c cubed over 3 factorial. Okay, so again, if it helps you, you can make a quick little table here. F of x was cosine x, f prime of x, negative sine x, f double prime of x then would be negative cosine x, and f triple prime is as high as we need to go on this guy, and that would be then sine x. So P sub 3 of x, and my apologies, these should be c's in here. So f of pi over 6, cosine of pi over 6 is root 3 over 2. F prime of pi over 6, sine of pi over 6 is a half, opposite of that would be negative 1/2. By the way, the x minus c to the various powers does still fit for this first one. X minus c to the 0 power is just a 1. All right, f double prime of pi over 6, cosine of pi over 6, root 3 over 2, so the opposite of that, negative root 3 over 2. And then we also have our 2 factorial in the basement as well, times x minus pi over 6 squared. And f triple prime of c, then we're at just sine of x at pi over 6. Sine of 30 degrees is half. So half. We also have our 3 factorial downstairs, x minus pi over 6 quantity cubed. So just a little bit of cleanup on those coefficients, and then we're ready to compare at various spots. So P sub 3 of x, I'll hang on to that root 3 over 2. We'll hang on to the minus 1/2 x minus pi over 6. Then we'll have minus root 3 over 2 factorial, remember, is still just 2. 2 by 2 is 4. X minus pi over 6 squared. 3 factorial is 6. 6 by 2 is 12, so plus a 12th of x minus pi over 6 cubed. So that is our P sub 3 of x. Now a little bit of calculator work. Pi over 6 in decimal form, approximately 0.523598775 is as far out as my calculator will show me. But we can see how close in these are if we look at, we'll just do the first couple digits. If we look at f of 52 hundredths versus P sub 3 of 52 hundredths. So cosine of 0.52, we get approximately 0.867819179, etc., etc., etc. B sub 3 of 52 hundredths, 0.8675192.856. So again, the first few digits are pretty close. So we get relatively close. The bigger the polynomial index you have, the more accurate a picture you'll have. And you saw that before with our progression from the 0 power polynomial to the first power to the second power even. The further out you go, the closer your curve is going to approximate the real thing. All right, so from 9.7, there we go. I would recommend 1 to 4 all, 5 through 9 odd, 13 to 29 odd, and on those, unfortunately the author was missing the left-hand side of the equation. I do need you to put the left-hand side of the equation as well. Let's see, and then 41 and 43. So that should give you plenty of practice. If you have any questions, please get in touch with me. Otherwise, stay safe out there, and I'll see you next time.